Welcome to another episode of solving exam riddles in organic chemistry. Today we have this somewhat more complicated starting material with a furan, an aromatic furan moiety, and this allylic alcohol connected by this alkyl tether. And as reaction conditions, we have catalytic amounts of protic acid and heating it up a little bit. Moderate reaction conditions. So, first step is we should think about where is this molecule preferentially protonated. It might be this aromatic system, for instance, at this position, then we get a cationic system that is mesomerically stabilized by this pi system. So we could draw some more mesomeric structures. Then this is an electrophile, and intramolecularly we would need a nucleophile, but this allylic alcohol is not that nucleophilic. Well, this might happen, but very simple, the reaction could also proceed into the other direction. It is an equilibrium reaction with, of course, the equilibrium by far on this side. On the other hand, also this allylic alcohol can be protonated. So here plus H plus, here plus H plus, then of course minus H plus here. So protonating here means we have in this first step the furan moiety unaffected. And here the allylic alcohol is protonated, and we get to this reactive intermediate. We have an water leaving group. So at the allylic system, let's assume that water is eliminated and also be regarded as an equilibrium reaction. And then we get to the stage of an allylic cation where the positive charge is distributed across these centers with a higher cationic charge at this center and at that center. So here we have delta plus, here we have delta plus, and an allylic stabilization of the cation. Okay, so we have electrophilic center here, we have electrophilic center there, and here we have potential nucleophilic center. Which one will react? Very simple. We should always think about either 5 or 6 membered rings are preferentially formed. Medium rings 7, 8 and 9, while this doesn't work very well. And smaller rings, then you have that ring strain evolved. Well, 5 or 6 membered rings. So from here, 1, 2, 3, 4, 5, 6, well, you have at least several membered rings, so we can skip that idea. That means this is the electrophilic center we should concentrate on. 1, 2, 3, 4, 5, either reacting here to give a 5-membered ring, nucleophilic center, electrophilic, but then this is de-aromatized, and if you draw that by yourself, you will see we have no chance for a nice re-aromatization just by eliminating an H+. Yeah? But if we let it react here, this is delta minus, here the delta plus. Let us connect these two centers. Then we have a 6-membered ring formed. The positive charge is stabilized mesomerically by the 3 electron pairs of the oxygen. Here is 1 hydrogen remaining, and on top there is this spirocyclic cyclohexene. Okay, how can we stabilize this? Also might be or is an equilibrium reaction. To stabilize that, it's just eliminating H+, so restoring the catalytic active acid. Deprotonating here will give us again the furan ring system re-aromatized and the spirocyclic cyclohexene moiety. So how would we call this type of mechanism? The OH group is substituted by the attack of a nucleophile, so we have a nucleophilic substitution. On the other hand, we have an electrophilic substitution of a hydrogen at the aromatic ring. So nucleophilic, but the nucleophilic part, it would be an SN1 reaction, typically for stabilized carbenium ions as reactive intermediates. But we should also think about, well, how would an SN2 reaction look like? Well, SN2 reaction doesn't have a cationic intermediate. Well, why not? Why not should the reaction take place directly from this intermediate, forming that one as a concerted process? Well, it is possible. With our information, we cannot decide, in this case, do we have SN1 or do we have an SN2 type process, but at least for the result that this molecule is formed, it does not matter, is it SN1 or SN2. This clearly is the preferred product of this reaction. Thanks for listening.